This is video 3 for the circuits unit. Let's talk about Kerckhoff. Kerckhoff is another famous scientist who studied circuits. Now, Kerckhoff's junction rule, it describes the conservation of electrical charge in the electrical circuits. So since charge is conserved, current must be conserved at each junction in the wire. We also have conservation of energy. So Kerckhoff's laws, we basically have two of them for circuits. The first one is all about conservation of energy. We have to think about this indirectly. We haven't really talked about energy, but we have talked about voltage. And remember that voltage is the energy per charge. So if I have a 9-volt battery, basically that means that each coulomb of charge that 9-volt battery has will have 9 joules of energy. So when we talk about energy in a circuit, really what we're talking about is voltage. So what that means then for Kerckhoff's first law is that the sum of all voltage drops in a circuit must equal 0. So this is Kerckhoff's first law. It also means that the voltage drop across each resistor must add up to being the voltage of the power supply. So here's a circuit, and I've got two resistors on it. I've got the first resistor, so I'm going to have the first voltage drop. So if I were to take something called a voltmeter and attach it parallel to this resistor, I'd be able to measure the voltage across that first resistor. And then I'd be able to do the same thing across the second resistor. And then for the battery here, I've got the EMF. So if I were to attach a voltmeter across that battery, I'd measure its EMF. I'd measure its voltage. So the sum of all voltage drops for a circuit must equal 0 according to Kerckhoff's. So the sum of all voltage drops for this particular circuit, I would have the EMF minus this delta V1 minus this delta V2 equals 0. So the EMF then it would equal that. Now you may be wondering, why is delta V1 and delta V2 negative? I honestly don't have a great answer for that. I guess it's just something where they are responding to the EMF, so that's why they're negative. Again, that's not a great example, but typically we say that the power supply or any battery or any power supply is positive, and anything that uses electricity like a resistor is negative. So maybe that would help out. This is also going to lead us to the idea of equivalent resistance. The equivalent resistance is the resistance of the whole circuit. So the EMF equals the total current times the equivalent resistance. So, using the equation we just derived, I can see that I have the total current times the equivalent resistance. Now, let's stop here and let's talk about current for a second. We have conservation of charge. So that means that the current that leaves this battery, that's going to be my total current, must also be the amount that's returning. So if I've got 12 amps leaving, I better have 12 amps returning. Well, let's take a look at this then. Since the amount of current leaving equals the amount of current returning, these resistors are not consuming any of that current. And that should make sense because all current is a counting game. We're just counting how many charges pass a point in the wire per second. So the resistors could slow that down. So if I lower the resistance, the current will become higher because the charges can move faster. However, it's not like the current is being used up. It's just that it's being slowed down or sped up. So what that means then is when I go to calculate delta V1 and delta V2, they both get the same amount of current, and that current is the total current. So delta V1 would be the total current times R1. Delta V2 would be the total current times R2. And notice then that the current cancels out. So then that the equivalent resistance equals R1 plus R2. So for a circuit where the resistors are in series, on the same line or on the same wire, the equivalent resistance equals the sum of all of the individual resistors. Kerckhoff's second law. This one talks about the conservation of charge. So for this one, the sum of all currents equals 0 at all junctions. This is going to allow us to study how currents are affected by circuits which branch off. So here we have another example here. I've got my battery, so my EMF. I could attach a voltmeter to each of these. So I would have like a delta V across this resistor and a delta V across this resistor. We'll talk more about that later. And now let's take a look at the current. Here's my total current. So the amount of current that leaves the battery should be the same as the amount of current that returns. But this current is going to come across a junction. Sometimes we call these junctions nodes. Well, that current is actually going to get divided up. I'm going to have, let's say, an I2 and an I1. And we can kind of think of this as like a fork in a river where the water gets divided up. Now, just like a river, the fork or the branch that has the least resistance will get the maximum water. So here, the branch in the circuit that has the least resistance will get the maximum current. So what we would find then is that the sum of all currents at this junction must equal 0. So the sum of these currents will equal the total current minus I1 minus I2 equals 0. So in other words, the total current is the sum of those two. And again, that's just at junctions. It's not like it's for every circuit all the time. It's just at junctions. Now, what's going to make this circuit cool is that the voltage drop across each of those resistors is the same. So you notice I did not put a 1 or a 2 beside the delta V's that I drew beside R1 and R2. That's because they're the same. And since there was no resistor before this junction, it's also going to be the same as the power supply. So if this is a 9-volt battery, I've got 9 volts across R1 and 9 volts across R2. The reason for that, these two resistors act as a voltage drop themselves. So basically they help satisfy conservation of energy that way. Okay, so here's what we see then. Here's what we see for the circuit. So V equals IR. So the total current would equal the EMF divided by the equivalent resistance. Remember, equivalent resistance is the resistance of the entire circuit. So, since I had total current equaling I1 plus I2, I'd have my EMF divided by the equivalent resistance equals that delta V over R1 over R2. And again, this is the important part. EMF and these delta V's are the same value, so they go away. And that would be how we calculate the equivalent resistance. We've got to remember to invert it. So for parallel or branching, the equivalent resistance equals the sum of 1 over the individual resistors inverted. And that will conclude video 3.